Okay, let's get started. Let's get started. Calm down. Things will be all right. We made a mistake over here, and one person noticed it. The direction of the acceleration is actually inside, so it is minus y, right? In this direction. The acceleration is this way because the force must be this way. So therefore, this equation, m dot theta double dot, must have a minus here, and must have a minus here, of course. Right? You understand? Because it is in the minus y direction. What I'm trying to say is that here, the net force, the centripetal force, has to be inside, and therefore the acceleration is towards inside. And because y is positive in this direction, this must be a negative sign here, this one here. Because this is the acceleration towards inside. Understood? So there's a minus over here. Please correct it in your notes. Minus here. Understand why that is? Minus here. I apologize for this, but it happens sometimes. So it's a minus. So therefore, there is a minus over here as well. Okay. So we said that the equations of motion are so great things because it somehow tells us what the future is going to hold for us. We will start here, and in the next 10 minutes I can tell you what's going to happen to theta. It's great. So, let's look at the movement in the x direction, because that is a little bit more interesting, the one in the x direction. So, let's look. I mean, you can look at both, but especially the one in the x direction is quite interesting. Let's look at the equation in the x direction. So that is equal to minus mg sine theta minus k theta dot is equal to m dot theta double dot dot L. Okay? We're going to look at this equation. So why am I looking not in the one in the y direction? The y direction is not too interesting. I mean, it can be interesting in different ways, but for our case, it's not. The other one is a little bit more fun to look at. Here's the reason. You need a certain centripetal force, and therefore a certain centripetal acceleration. And that will be provided by minus t plus this weight. So the t, the tension in the rope, will increase or decrease in order to satisfy this rotation. So if you rotate it faster, you need more tension in the rope. If you rotate it slower, you will get less tension in the rope. So that's all what there is. Okay? But what's interesting is the movement in the x direction, because that way I can tell you, if I leave it here, how long it will take to come back here, because that's all happening in the x direction, not in the y direction. So that's why I'm looking at the x direction, okay? It's a bit more interesting. There was a good question during the break. Someone said, well, we are writing these equations with respect to the observer outside, right? That's what the Newtonian frame is. But he says, the coordinate system is also moving. Yes, it is moving. Doesn't matter. As long as the equations I write hold at every instant, I'm fine. And I'm claiming that these two equations that I wrote here, this and this one, they will hold at each instant with respect to an observer who's outside, although the coordinate system is rotating or moving. It will still hold. So if you convince yourself that the coordinate system is moving, but these equations are still there and they hold, then we are fine. Yes, sir.
On the
Let's try to do it in English, because it's a good exercise.
There is a theta with dot.
Yeah. This one? Yeah.
This must be, I think, only theta.
No, this is not friction. This is not a spring. It is a friction. And friction is only there if there's a theta dot, basically an angular velocity. Okay? It could have been a spring, but if it was a spring, it would still oscillate forever. Okay? I wanted to make it a friction so that it actually stops at the 0 point. Okay. Friction, yeah, that's quite important. Okay? Good. So this is that. So we are looking at the one in the x direction. So this one is quite great because it will tell us the movement of this pendulum. So what you're seeing here, you're seeing a second order differential equation. Okay? A differential equation is really great because it shows equations in such a compact form. If I would be very interested to see what is theta t as a function of time given a certain theta 0 and a certain theta 0 dot. I mean, basically an initial condition. I mean, where do I start? And then what's going to happen to theta as a function of time? It would be so nice to see what's going to happen. But if you write this equation, if you try to solve it and write theta t is equal to blah, 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 you might get something so complex that it would be a really complex equation. I mean, if you just write theta as a function of time, and that's what I really want actually, right? I want theta as a function of time. I don't care much about differential equations. I really want this. But this will, believe me, look quite complex. And look how compact this equation is. It's a second order differential equation, very compact. Okay? And that's why this differential equation is so great. But then you take the differential equations class to solve the differential equations. Basically, find theta as a function of time because I'm interested in theta. Okay? If I give you a differential equation with respect to an airplane, you might not immediately understand what the airplane is going to do. But if you write the movement of the airplane as a function of time, then you can say in the next 10 minutes this is going to happen. That's why you need to solve these equations to see what's going to happen. Okay? But the solution might be quite complex, so that's another story. All right? So if you have something like this, we need to do something to help us understand it better. And what we very often do is we simply divide this equation into two parts. In other words, we divide a second order differential equation into two first order differential equations to make it easier to understand. Just simple as that. So what we say is, let's define two variables. Theta 1, we call that theta, which is the angle. And I define another variable, theta 2, which I call theta dot. Theta dot is the angular velocity of that mass. Okay? Two variables. So if you do that, then you can simply write the following. Let's take this differential equation and say theta double dot, right? You can do that. Theta double dot is equal to minus g divided by L times sine theta minus k divided by ml times theta dot. Right? Just rewriting that equation. And then you can simply say theta double dot is equal to theta 1, theta 2 dot, theta 2 dots, because theta double dot is that, right, is equal to minus g divided by L times sine theta 1, because theta is equal to theta 1, minus k divided by m L times theta dot, which is equal to theta 2. Okay? So it's just the same thing with these new variables. And you can also say theta 1 dot is equal to theta 2. Right? It comes straight from these equations. Because if you take the derivative of theta 2, I'm sorry, of theta 1, it will be equal to theta 2. So these are the two differential equations now. They are both first order. Two first order differential equations. Still the same thing. Nothing really special. Nothing really special. And we call these variables, theta 1 and theta 2, are so-called state variables. They are called state variables. Why? Yes? Question?
Don't we have minus in the x direction equation
Which one?
on the table?
You mean here? You mean this one? Why? You mean over here? No, because x is positive in this direction, and this one, maybe this one, I want to call a positive theta. If this is a positive, that's a good question actually. If positive theta is in this direction, then x will be positive, then it will be positive on that side as well. Okay? So this one I will call a positive theta. It's a good question. Okay, so these are state variables. Theta 1 and theta 2 are called state variables. Very important idea. Why are they called state variables? Because they define the state of the dynamic system. It defines the state. What is the state? Durum. Turkish durum. Durumu anlatıyor. State variable. Okay? So, what do I mean? If I give you a picture like this, what will you say? Well, it has a certain theta, which is equal to theta 1, but it might also have a velocity in this direction or that direction. We don't know from that picture because it's an instantaneous picture. And if you give me theta 2, and then if you give me theta 2 dot on top, you pretty much tell me everything. You tell me the acceleration, you tell me the velocity, you can tell me the position. So given these three variables, you tell me everything about this dynamic situation of that picture. So if you just give me this picture, I don't know, something like that, this picture, and tell me theta is 30 degrees, it doesn't tell me the whole situation. Right? It's just a picture. It doesn't tell me the whole situation. I will say, does it have a velocity? I mean, it must have a velocity going up or down. I don't know. Does it have an acceleration? So then I will ask you, how many variables do I need to fully define the situation in this picture? Well, it turns out I need two variables, theta 1 and theta 2. And theta 2 dot, if you give me that, I give you also the acceleration. So these two variables are enough to define to me the situation of this, to describe the dynamic system. Therefore, I call them state variables. The variables that define the state. So the question would be, how many state variables do I need to fully define the dynamic behavior of this pendulum? Well, according to what we are doing, I mean, in that framework, we are needing two. Question, how many variables do I need to define the exact situation of an airplane in space? How many state variables would I need to define the movement of an airplane, the dynamic movement of an airplane in space? Something like that. We will see. Okay? Obviously, we need more. But that's a very important information, because that means if you just give me the velocity of the airplane, it doesn't tell me the whole picture. Maybe the airplane is going straight, but it's going backwards. Right? You need the angles. Maybe it is backwards, but it is rotating, so it's fine. Maybe it will rotate back. So you need the angular velocity as well. You see? So state variables, the number of state variables defines how many variables I need to explain to me the situation of that thing. And when I say state variables, don't forget what it means. State variables means the variables that I need to describe the motion, the dynamics of a system. And for this one, I need two, theta 1 and theta 2, and they are the state variables. So I would love to have this, theta 1 and theta 2, and write them as a function of time and see what they are doing as a function of time, 10 seconds, for instance. If you can tell me this, it's great. You tell me everything about the motion of this dynamic system. Okay? So I need these dynamic variables. Okay. So, two equations, two state variables. I have this. Good. Next point. Next question. This dynamic system has a very interesting point. I mean, this thing will swing around left and right, and eventually it will come back and stop here. So this one here, this point here, where theta is equal to 0, and theta dot is equal to 0, right? Or theta double dot is equal to 0, is an interesting point, because this is like the resting point. It is very different from those other points, right? I mean, you know, this is another point for the pendulum. But we all know it's going to come back to that point. So anywhere you start, it will come back to that particular point. And this is the point. So for instance, you know, this might be a point where theta equals 30 degrees, theta dot is equal to 10 degrees per second, and theta double dot is equal to 0. That's another point. It describes the state of this dynamic system. This describes another state of the dynamic system, right? You might have something else. You might have something like this, right? Very like this. So theta equals, I don't know, 80 degrees. Theta dot is equal to minus 10 degrees per second, and theta double dot is equal to 0. That's another state. This is a state described by the state variables. This is another state described by the state variables. By the way, this is theta 1 and this is theta 2, right? So theta 1 is this, theta 2 is that, and this is theta 2 double dot. Or, I'm sorry, this is equal to theta 2 dot. So what you're seeing here is there's three different states of this pendulum. This is one state, this is another state, this is another state, and you can define many other states. So it moves through the state. And I can describe the states of that vehicle, of that dynamic system, using the variables. But out of all these states, this one is quite special. The reason it's special is because eventually everything will converge to that point. Regardless where you start, you will always end up here. It's like death. Regardless where you start, everyone's going to die, right? It doesn't matter where you start or what your initial condition is. Final point, death. Very important point in life, isn't it? It's the same here. It's a very important point among the state variable, among the states, is that particular point. What is special about that point? Why is it so special? It's an equilibrium point. It's an equilibrium. What does an equilibrium mean? Derivatives are 0. What?
Point where it will go at the infinity.
It will stay there forever if you don't touch it. If you touch it, it will move. It will stay there forever if you don't touch it. So it is the state where if you don't touch it, it will stay forever. That's what we call an equilibrium point, and we are very interested in these points. So we call it the equilibrium point. Of a dynamic system denotes a steady state on which all states state variables, I'm sorry, all state variables don't change or stay constant in time with no input. If there's no input, that's an equilibrium point. Very special point. We love equilibrium points. You don't touch it, it will not move. Yes?
So this is the case of a stable equilibrium?
No. Well, this one might be. This is a stable equilibrium point, but we will talk about this in a minute. Okay? We'll talk about this. But if it's something is unstable, doesn't mean it's not an equilibrium point. Equilibrium point is a point, if you don't touch it, it will stay there forever. Yes, sir? This one? Yeah, probably out of battery. Yeah, that's life. Can you hear me? Yeah, okay. We have a different microphone, don't worry. It's all taken care of. You understand? Is that fine? Just because an equilibrium point is not stable doesn't mean it's not an equilibrium point. That's something we'll talk in a minute, but you understand the point of an equilibrium point. You don't touch it, it will not move. It will stay at that state forever. Okay? Don't touch it, it will stay there forever. So in this case, this is a special equilibrium point. This is a special point, it's an equilibrium point. If you don't touch it, it will not move. If you touch it, it will. And that's what we call an equilibrium point. Now, equilibrium points are very important. We love equilibrium points. Okay? For example, an airplane flying at a steady velocity in space. That's an equilibrium point. If nobody's touching it, it will stay there and it's going to go forever and ever. We love equilibrium points. We love equilibrium in life, right? You want to be in equilibrium. If nobody touches me, I'll be fine. So we like to investigate equilibrium points. So how do we find equilibrium points? Let's do that. We can look at equilibrium points. If you have these equations, these two equations, the equilibrium point can be found when everything is going to be steady state. Denotes a steady state in time, so the state variables are not supposed to change. It also means that theta 1 dot is equal to 0 and theta 2 dot is equal to 0 according to those equations. Right? Because it means as a function of time, the state variables will not change, and the state variables are theta 1 and theta 2, and therefore theta 1 dot is 0, theta 2 dot is 0, obviously, right? So they are not changing. So if you take these two equations, it's actually quite simple. You put this into these equations, try to find, for instance, like this. Theta 0 is equal to minus g divided by L sine theta 1 minus k divided by ml times theta 2, and 0 is equal to theta 2, right? This was equal to theta 2 dot, and this one was equal to theta 1 dot. So they are both equal to 0. Okay, so this is what happens in steady state. This is what happens at the equilibrium point. So first solution is right here. Theta 2 must be equal to 0 at the equilibrium. So mathematically I can find this. And the second one is this second equation here. 0 is equal to minus g divided by L sine theta 1 minus k ml times 0, right? So this is gone. This is gone. Which means sine theta 1 must be equal to 0. So that's your second condition. And theta 1 is what here? Is 0. What else? And what? pi, good. 180 degrees. So I found two equilibrium points, actually not one, but I found two. Right? Better rewrite it. This is in degrees, so write 180 degrees. So which means we found two equilibrium points. This is one equilibrium point, and it looks like this is another equilibrium point. Hopefully this is a rigid rod, so that it can actually stay like that. If it's not rigid, it will just fall down, of course. But if it's a rigid rod, this is another equilibrium point. And I found this mathematically. I didn't even have to think. I mean, as I said, you ask any kid in school, he will say, oh, this is an equilibrium point. Because if you don't touch it, it will stay there. Everything converges to this point. It's an equilibrium point. But I found it mathematically. This is the beauty. Which means next time I can find the equilibrium point of an airplane flying in space. Not in space, in the atmosphere, of course. I can find it mathematically. Okay? It is not always obvious at what angle the airplane must fly. What is the angle of attack in a steady flight condition? Lift, drag, blah, 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 all this. But I can find it mathematically in 6 degrees of freedom. So that's beautiful. I can find equilibrium points. In this case, we found two equilibrium points. One is this one and one is this one. Do you agree that this is an equilibrium point? This one here? Some people say, nobody will understand other than the Turkish people. They say, is this an equilibrium point? Yes. If you don't touch it, it will not move. But if you touch it just a little bit, it will swing to the other equilibrium point, right? So, if you don't touch it, it will not move. If you touch this, it will again move a little bit, but it will come back to this point. So, equilibrium point 1, equilibrium point 2. It says two equilibrium points, not 1, 2. What is the difference between these two? You touched it, it goes away. You touch it, it will go back to the same point. What's the difference? Stable and unstable equilibrium points. This is a stable equilibrium point, and this is obviously an unstable equilibrium point. That is the difference. So, if I ask you a question, is the pendulum stable? What would you say? Is the pendulum stable or unstable? What would you say? There is no answer to that question. The answer is the pendulum has two equilibrium points. One is stable and one is unstable. Stability is not a property of the system. It is a property of the equilibrium points. So I can ask you, is this equilibrium point stable? And you might say, yes, it is stable. Is this equilibrium point stable? You might say it is unstable. Is the pendulum stable? It's a meaningless question. Okay? So you might hear something like the F-16 is unstable. That's a wrong statement. The correct statement would be the F-16 has equilibrium points that are unstable. In fact, some of the equilibrium points of the F-16 might be stable. Okay? So, stability is a property of the equilibrium points, and don't forget that.
In this problem, we said the velocity is 0 and the acceleration is 0 in order to find the stability points and equilibrium points. But in an aircraft flying on the atmosphere, we cannot say the velocity in x, y, or z direction is 0. How can we find the equilibrium point on that situation?
I didn't say the velocity has to be 0. It turns out from these equations that a velocity must be equal to 0. I'm not even saying that, because my equations these are the equations that describe the motion of my system. And if I say these are my theta 1 and theta 2 are the state variables, and if the definition says that the state variables must not move, then theta 1 dot and theta 2 dot must be equal to 0. And if theta 1 dot is equal to 0, it turns out that theta 2 must be equal to 0. It is a consequence of my definition of theta 1 and theta 2. Okay? So if, for example, theta 2 was not, if this equations would be in a different way, it could have been that the velocity must not be equal to 0. So it doesn't mean that the equilibrium point always means velocity equals 0. It just turns out from these equations that theta 2 must be equal to 0. Is that okay? Yes, sir.
Do equilibrium points change with time?
That's a good question. Equilibrium points, if the system doesn't change, the equilibrium points don't change. So think of an airplane. Airplane has a lot of equilibrium points. One velocity is one equilibrium point, another velocity is another equilibrium point. We will talk about this. If it makes a turn, you might consider it an equilibrium point, things like that. Will the equilibrium point for a certain velocity change? The answer is no. But if you're burning fuel, the location of the center of gravity changes, then it will change too. But if the system is fixed, the equilibrium points are also fixed. You can see it in these equations here. We wrote an equation for this particular dynamic system. As long as these equations exist, then the equilibrium points are fixed. These equations will only change if the dynamic system will change. For example, if K will change, if the mass will change, if the length of the rope will change, then these equations will change, and therefore these will change. But if they don't, the whole principle is consistent. We start Newton's equations, we put the equations down, we put the differential equations, find the equilibrium points. They will never change as long as those equations hold. Good? Any other question? Okay, now one more definition that's important. We talk about stable and unstable, okay? And obviously everybody understands, it is diverging, it's not coming back to its original point, therefore it is unstable, right? That's the definition. Stable means that you perturb, it will come back to the stable equilibrium point. Okay, so that's good. But this type of stability is called static stability. This behavior or this property is not only stability, stable, unstable, it also is, more specifically, this is called static stability. Static stability. In other words, when we are talking of the stability of these points, the way we have been talking now, we are really talking of static stability. So static stability is the initial tendency of the system to return to its equilibrium point after it has been perturbed from it. So we call this static stability. Static stability is the initial tendency of the system to return to its equilibrium point after it has been perturbed from it. So this is the equilibrium point. I'm going to perturb it and we'll see. If it comes back to the equilibrium point, we call it statically stable. Or if it doesn't come back, we call it statically unstable. And we will talk about this in a month in a lot more depth, so don't worry about it now. But you have to understand that this property is called static stability. So if there's a static stability, there must be a dynamic stability. Okay? So what is dynamic stability? Dynamic stability basically talks about the fact that, doesn't only talk about the fact, does it come back? It talks about the fact of how does it come back? How does it come back? Does it take a few seconds to come back? Or does it take an hour to come back? Or does it take 2 years to come back? Same thing with instability. We know we push this thing, it will immediately diverge. But there are cases where you perturb it, it diverges, it diverges to another point in a few seconds, but it might diverge in hours, weeks, years. If it diverges in years, nobody cares. It's practically not moving for us. For humans who only live 70 years, right? A movement of years is not really that significant. But if it diverges in a second, then that's important. So how long does it take to diverge, or how long does it take to come back to the equilibrium point, is a matter of dynamic stability. And that is sometimes more important than static stability. Static stability only says, if I touch it, it will go away from the equilibrium point. It will never come back. Good. But how long does it take? Same thing with this one. If I disturb it, it will come back. Yes, that's great. But how long does it take? How much do I oscillate? Think of an airplane. You're flying at steady flight. Okay? Equilibrium point. Wonderful. Everyone is happy. And then you have a little gust, and the airplane starts oscillating. How long does it take to finish that oscillation? Does it take a minute? Hours? How big is the oscillation? What's the period of the oscillation? Is it something like that, so everyone will throw up? Or will it be something like that? Really smooth, nobody will feel it, and people still can eat. Both are stable equilibrium points. One is acceptable, one is not. Think of an airplane that's unstable. So you're flying like that, you have a little gust, and the airplane goes, oh, unstable airplane. Nobody likes that. However, if the equilibrium point is unstable and the airplane does this, slowly goes back, and it takes hours to actually go to 10 degrees, and you have to wait a year until it is 90, nobody cares. It can be an unstable equilibrium point, but it takes so long to diverge. And that is the topic of dynamic stability. Okay? So that information, is an equilibrium point stable, unstable? Tell me about dynamic stability. F16 is unstable. How many equilibrium points are we talking? Right? If I have 100 equilibrium points, 2 of them are unstable. Okay? Then I don't go to those equilibrium points, I stay in the 98, other 98%. So, understand that? If you tell a dynamic system is stable, unstable, doesn't mean much. We need to understand which equilibrium points, how many equilibrium points are stable, unstable. And when I say stable, unstable, we need static stability. More important to me is what is dynamic stability. If it's unstable, how unstable? Stable, how long does it take to come back? Does it oscillate? Is it fast? What's the period? What's the frequency? Those kind of things. What's the amplitude? Halving time, doubling time, those kind of things. So those are all dynamic stability properties. Okay? And when I say stability, I usually talk about an equilibrium point. The good thing about all this is that the equilibrium points can be found mathematically when I write the equations of motion. It's perfect. So I start from F equals ma. So this Newtonian frame of work is so great. It helps me in a lot of ways. I start with F equals ma, holds everywhere. The observer has to be outside. Then I write these equations. I get differential equations. I need to solve them somehow. Find equilibrium points. And now I can look at stable, unstable. Okay? So, what do I do next? I have an equilibrium point, and I would like to... Great, we have a lot of time. I would like to do the following. I would like to use my equations. These are the 2 equations. And I would like to analyze the stability of this equilibrium point. Is it statically stable or statically unstable? How do I do that? How do I look at stability of an equilibrium point? You must have learned something in system dynamics, right? So how do you do that? Just Just say something. How do you look at stability? Something is stable, unstable. What do you do? Root? Roots what? What? Characteristic equation. Okay, that's a good word. What else? You look at the characteristic equation. Good. What's a characteristic equation? Denominator of the transfer function. Good. What's the transfer function?
Output divided by the inputs.
Okay. So how do I divide output input? But it's in a certain form, right?
I think we can also look at the small perturbation and observe the results.
Good. So we give a little observation, we give a little input to this. Basically, I give a little force, I touch it somewhere, and then see what theta 1 and theta 2 does. If everything goes back to equilibrium, we say it's an equilibrium point. It's like testing the system, right? That's one way of doing this. So basically what you can do is you can add a little force over here, right? A little force, a little perturbation, and then this goes of course in the x direction of your force equation. Give a little force and see what happens, right? That's one way, and that's good. It makes sense. Give a little force, see what happens in time. I like the transfer function idea, but we are stuck. What's the transfer function? How do I get the transfer function? So find the transfer function now. How do I find it? Laplace. Okay, I need Laplace. What's Laplace? So I need to do Laplace to this one, right? Can I do Laplace to this equation and find the transfer function? What? It's nonlinear. Oh, very important. It's a nonlinear equation, so I can find Laplace. Is that right? You can find a Laplace transform to this, but it will not be a transfer function. Transfer functions are defined for linear systems. So this is it linear? Why? We have the sign here. As long as you have this sine function here, this is nonlinear. So what do? We are stuck. We have to linearize it. How do you linearize an equation? What? Taylor expansion, Taylor series expansion. Is that how we do it? Okay, let's do it then. We want to look at stability, right? So let's do it. Let's do Taylor series expansion to linearize this thing. Can you linearize it? How do we linearize it? We want to linearize this part of the function. Can you already see what the linear equation of these would look like? Someone says cosine. Yeah. How about if it's between 0 and 5 degrees? Okay, my assumption is 5 degrees. Would that work? Will it? Or no? How about 4.8? Let's make it a deal. 4.4, 4.5. Okay, let's put it another way. You mean if it's a small angle, sine theta 1 is actually equal to theta 1, and therefore I can make a small angle assumption and put it there, right? That would be fine. That's actually true, so you can just remove this, make it theta 1, it will be a linear equation. But let's do it the formal way, okay? Let's look at Taylor series expansion. So, what does Taylor series expansion say? That's to linearize the system, the equations. So how do I do it? Taylor series says this. If you have a function, let's say y is equal to f of x, okay, let's say you have a function like that, then you can linearize the function, or you can approximate the first few terms of that function will be a linearization. So here's my question then. Let's say this is y, and this is x, and this is f of x. Just one function. I don't know what. What is a linearization of this function? Now I want to linearize this. I want to linearize f. What is a linearization? Let me ask a question then to the class. Would that be a linearization of that function? Yes, because it looks linear. Will Taylor series will give you this? Don't say yes or no. No, why not?
Because we need the 2 points.
2 points.
We know the solution or equilibrium point, we can say that, and the other one we want to find.
I'm just, no, forget about what we have done now. I have one function, y is equal to f of x. I'm trying to linearize the function f. So I'm just saying, is the red line a linearization of that blue line? Should be okay, I make it continuous for you. Fixed point. Initial point. Should start, okay. Is it a linearization of that function? Will Taylor series will give you that red line?
Not exactly,
Not exactly. What will it give?
because we need to expand it for infinity, so we cannot do that because of that. We will have small fluctuations, but not straight numbers.
Okay, I'm just saying if you use the first few terms of the Taylor series, which will give you the linear part, will it give you this red line?
It's an approximation. We can approximate it which way we want.
Good, so this is good. Yes?
If you are expanding Taylor series expansion around the equilibrium points, you can get a linear function.
Yeah, but don't think about the equilibrium points. Just look at this. I mean, this is now a different problem. Y is equal to fx. We'll talk about the equilibrium point thing, but y is equal to fx. X is y is a function, you know, the output of the function, x is the input, and f is a function, and this is the relation. So I'm just asking, I want to linearize f. Will I get the red line if I do the Taylor series expansion, the first few terms? Yes, sir.
Taylor series use the slope at the first point and of the end.
Which point?
The first point of the end.
This one?
Yeah.
The slope is this one. Is it going to use that?
And then approximates. So if you add more terms, it gets the.
Okay, but I'm just going to use the first few terms. And then if you use this slope, you will get this line, which is different from that one. So then the Taylor series will give you this, not that. So which one is it?
Depending on how many terms you use.
I'm going to use one term, the first few terms, the linear ones. So I'm just going to get this. If I get more, I will actually get a curve. I will not get this line. The line is only the first two terms, right? Taylor series. Any other comments? Yes, sir.
And we should decide the point to linearize.
Ah, that's important. We need to find a point around which we want to linearize this thing. Right? Okay. So the Taylor series linearizes a function around a point. What I plotted here is an approximation or maybe an average, a curve fit of that line. It is linear, but it is not a linearization around a point, and the Taylor series will not give you this line. This line will be an approximation, a curve fit of this blue line. The Taylor series will do this. It will choose a point and then put a line around that point so that in the small neighborhood, it will approximately be the same. I mean, the first few terms of the Taylor series expansion. If you use everything, it will just approximate the whole curve. But if you just use the first few terms, you will just get this little line. So in other words, if you choose this point, then you will get this line. So that's a different line. This is a different line. That's a different line. You choose this point, you will get actually this line, which is very different from everything else. If you use the first point, you will get this line. So Taylor series will linearize a function around a certain point. You first need to find that point, or whichever point you choose. You can if you choose this point, you will find this, and this will be here. If you choose this point, then it will be linear, I mean it will be an approximation of that function in that little neighborhood. If you choose this one, it will be here. If you choose this one here, it will be the same, but if you go away from that point, it will obviously not hold anymore. You understand? So, you give me a function and you ask me to linearize it. The first question is, around which point do you want me to linearize it? And then I choose the point and I will use that to find that equation. So, the Taylor series expansion is simply y is equal to f x0, x0 being the point you want to linearize it. Let's choose this point and say this is x0, this point. And this point here would be f of x0. Okay? This is getting too crowded. Let me plot it again, which basically means you have x, y, this is your curve. Choose a point, let's choose this one here. Let's say this is x of 0. I'm choosing a point on that function. And this one will be f of x0, right? So y is equal to f of x0 plus del f del x, x minus x0, which means del f del x, which is calculated at x equals x0. So which means find the slope of x at x0, the slope is this, right, f del x, and it is a number because it's calculated at x0, so it is a number, so I know what the slope is, times x minus x0. So x is any variable that comes from here, so this is here, this could be x. And then you of course have the higher order terms for the Taylor series expansion, but if we want to linearize something, we only use this part, and that is your linear approximation of the system. So what do I have now? I have this y is equal to f of x0, which is a number, plus del of f del of x, x equals x0, which is another number, times x minus x0. x0 is a number, x is the only unknown here, or the variable. So I have another y, g of x, where g is actually a linear equation. And the whole system is a function of x. Okay? So this is what Taylor series expansion is about, and this is what linearization is about. Finding an average is not a linearization. Finding a point and putting a line at that point is linearization. Okay, so I will put a homework on the website. You don't have to submit it. It is just to satisfy yourself, to understand that when we take Earth as an inertial frame, you will not make a big of a difference if the velocities are small. Next week we will continue with this and look at the linearization of our equations to analyze stability of the equilibrium points. Okay, see you next week.